All right, so what does continuous mean? Continuous is going to be really important when you get to calculus. It just means there's no breaks in the graph. So a function can be continuous at a certain point, or it could be continuous on an interval, or it could be continuous everywhere. So continuity at a point. A function is continuous if three conditions are met. The function has to be defined. So this function is not defined at x equals 2, right? Because if I plug in 2, I get 0 in the denominator. So it's not continuous there because there's a hole in the graph. You'd have to lift your pencil up. So it's kind of different ways that you can check for continuity. So the first is you can check for continuity at a given point. Step 2, the function would have to have a limit at that point. So in this case, it's not continuous because it doesn't exist at that point. There's an asymptote. So basically, holes and asymptotes end up failing continuity. So there's nothing to write here. I'm just kind of reading it to you. But number 3, the limit at that point has to equal the value of the function at that point. So first, it has to be defined. The function has to have a limit, can't go in two separate directions, and the limit and the value should be the same. So in example 3, if I just look at the graph, see how from the left and the right, I'm approaching, what is that value, 7? But what is the value of the function at that point? It's way down here at -3. So even though the limit is approaching the same value, there's still a hole in the graph and it's somewhere else. So we're just going to take a look at, kind of proving that the function is continuous. I think you can see for all of these different graphs, the function's not continuous, right? Not continuous at 2 because there's a hole, not continuous at 3 because there's an asymptote, not continuous at, what's this one, x equals 4 because the limit exists, but the function exists at a different point than the limit. So just 3 ways that it failed continuity, basically. And then the next page just mentions continuity on an open interval. So the function is continuous on an interval if it's continuous at every single point in that interval, which I think is just wording it more complicated. But as long as you don't have to pick up your pencil, it's continuous. Here's something that is a little bit new. So there's 2 types of discontinuity. One is called removable and one is called non-removable. So I just wanted to kind of plant the seed a little bit about this vocabulary so that when you get to calculus, you've at least heard of the word continuous or discontinuity or removable versus non-removable. So a removable discontinuity is called removable because it could be made continuous by just appropriately defining or redefining the function. So here are some removable discontinuities. So I could just tell the person, all right, yeah, there's this hole there. It has a removable discontinuity at x equals 3 because all I have to do to fill in that hole is say that f of 3 has to be 5. So basically, holes are considered removable. This one has a removable discontinuity at x equals 4 because all I have to do is tell the person, oh, at 4, you just have to say f of 4 is 3, and you'd fill in that missing point. And same thing over here. This is a removable discontinuity. It has the function way up here. All you have to do is say, hey, f of 0 is -2. So this has something called a removable discontinuity at x equals 0. So holes are removable because we can just tell someone what the hole is. A non-removable discontinuity, we can't redefine the value, and they're caused by usually asymptotes. So there's no, I can't tell you what the value is at 3 because this one is shooting down towards -infinity and this one is shooting towards +infinity, and I can't put a value in between so that I don't have to lift up my pencil. Here, if I give you that one defined value, I could go the whole way without picking up my pencil. There's no value here that I could tell you so that I could bridge these 2, parts of the function. So it's called non-removable, and this one is at x equals 3. This is a piecewise graph. So even if I tell you, one given value, I could never bridge these 2 sections of the graph. It's just too much. It's a non-removable discontinuity. I could never make my pencil go from here to here without picking it up. So this is considered a non-removable discontinuity at x equals -3. So just recognizing that holes are removable and asymptotes or piecewise functions are non-removable. Not a big concept for your, test on Friday, but just like I said, planting the seed for calculus. Continuous is something you'll talk about in calculus. So just here are some functions, and I wanted you to decide if they have removable or non-removable discontinuities. So, and it just says, how do I detect them analytically? Analytically means using algebra when you can't just look at the graph. So it said you're going to find the restricted values for the function. So like what can x not be? And if these values can be eliminated by some technique, the discontinuities are removable. However, if the values cannot be eliminated, then the discontinuities are non-removable. So this is a good review of rational functions that ties in with limits. So if I was going to look at the first one, let's think about it, first of all, analytically. What is the problematic value for x? X can't be what value? 3. So at x equals 3, do we have a removable or a non-removable discontinuity? It's non-removable. And it's non-removable because it's an asymptote. So because you've got a final exam coming up, let's take a minute to remember how to graph 1 over x minus 3. We already know it has a vertical asymptote at 3. Do you remember the other steps to find a rational function? Look for the x and y intercepts. This will have no x-intercepts because the numerator doesn't have any x in it. So the numerator set equal to 0, that would have been your x-intercept. When you plug in 0 for x, you get your y-intercept. So this would have a y-intercept at -1/3. So you can plot -1/3 on your y-axis. And remember the horizontal asymptote rule. If the denominator has a bigger power in it, it will approach 0, right? Because the denominator is going to blow up. So this will have another asymptote at y equals 0. So you can see that the bottom part of the graph is kind of going this way as an elbow. And then we would have to plug in one value over here. So if I plug in the value of 4, I would have 1 over 1 is 1. So 4, 1 is another point that lies on this rational function. So you can see that at x equals 3, it's a non-removable discontinuity because it's an asymptote. So what happens in number 2? I should see if x equals 2 is going to be removable or non-removable. I know that 2 minus 2 is 0. That gives me 0 in the denominator. So I try to factor the numerator. So how would I factor this? So it's going to be x times x. I'm looking for the factors of -6 that add up to 1. So it sounds like it would be x plus 3 and x minus 2. So the x minus 2 is just canceled, right? So it would be removable. And if I was going to graph this function, this is just a linear function now, right? Y equals 1x plus 3 is in the numerator. So it would start at 3 on the y-axis, and it would just go up 1 over 1 as a line. And I need to put in that removable discontinuity is going to be a hole, right? So it looks like the value is at 2, 5. That's a hole right there. I should have marked it first, but so 2, 5 is a hole, but it's removable. I could just tell someone, hey, at 2, put a dot at 5, and then it would make the graph continuous. Why don't you see if you can check out number 3? See what the undefined value or values are, and are they removable or non-removable for number 3? There's actually going to be 2 different values that you have to discuss. So I factored the denominator using difference of squares, and I canceled my x plus 4s. So that gives me a final function of 1 over x minus 4. So that makes positive 4 the undefined value that's non-removable, because that's an asymptote. And at negative 4, I could plug that in and get negative 1/8. So that's considered a removable discontinuity because it was a hole in the graph. So this is a little bit dark, but you can see I've got my asymptote at positive 4, my intercept at negative 1/4, my hole is at negative 4, negative 1/8. It's a little red circle right there. So the graph is extending like this elbow and then up here like this elbow. So some functions might have more than one discontinuity. So in this one, it had one hole and one asymptote. So it kind of ties together our study of rational functions with this end unit on limits. So if you could take a couple minutes, actually, maybe I'll do these with you because I want them in the video anyway. And some functions don't have any discontinuities, right? So example 4 is just a linear function, right? So it is continuous everywhere. So you could either say that it's continuous everywhere, or you could say there's no discontinuity, right? This is just a straight line. It has a y-intercept at 3 and a slope of up 2 over 1. So some functions are continuous. Most of the functions we've studied are continuous, right? Exponential functions are continuous. Quadratic functions are continuous. Linear functions are continuous. Number 5 is a piecewise function, kind of like the we did it about chocolate, and if you bought less than 2 pounds, it was this function, and 2 or more pounds, it was this function. So the way that you want to examine this for discontinuity, and then we can graph it over here, you want to look at the values where there's going to be that break from function to function, and you actually want to plug in 0 into each function to see if you get the same result, because that means the graph is going to touch each other at that point. So even though this says x cannot equal 0, I still want to plug 0 into this function to see what I get. So when I plug in 0 in this top function, I get 0, 3. When I plug 0 into this bottom function, I get 0, 5, because it's a constant function. So it's going to be a jump in the graph. So what I want to do is I want to look at what the graph looks like. So are they lines that are too far apart, or is it just a line that has a hole in it? So let's see, 2x plus 3, we already did that one up top. So let's just graph, as long as x does not equal 0, it's just this straight line, 2x plus 3. So I'm going to start at a hole on the y-intercept, right? So 0, 3 is a hole. And then I go up 2 over 1 in this direction and down 2 over 1 in this direction. And what's the only thing that's happening? At 0, they want me to put a dot at that one point, right? Only when x is 0 do I put a dot at 5. Oops, I'm on the wrong graph. Here we go. So would you consider this to be removable or non-removable? So can you do one thing to make it continuous, or will that one thing still have a break in the graph? What do you think? What would you call this one? Yeah, I would call this one removable. If I just redefine that one point to fill that hole in, I've got a continuous function. So I would say at x equals 0, we've got a removable discontinuity. So just using some math vocabulary to talk about a function or a break in the graph. So that one was removable. So let's try this last one. I still have that same function, 2x plus 3, and this time x cannot equal 0. And then this function is negative x plus 3. And this is when x does equal 0. So I just want to plug in 0 in each of these functions and see what I get. So in the first function, I would get 0, 3. And in the second function, I would get 0, 3. So actually, this function is going to be continuous because even when I jump down here to the other function, it's going to fill in the same value that I was missing in this top function. So this one's actually going to be continuous everywhere. So I can just graph that line 2x plus 3 and just extend it forever because it fills in that hole, right? At 0, if I put a hole, I'm going to be filling it back in with 3 anyway. So I don't even have to show that there's a hole there. It's just a straight line. So the type of piecewise function that I left out, I guess, on this set of notes that maybe I should do next year, if you had like 2x plus 3 when x is less than 0, and you had something like 4x, I don't know, plus 5 when x is greater than or equal to 0, they would be going like you'd have a separation in your graph because this one would be, here's this going this way. And then if I start at 5 and have a slope of 4, see how I'm going this way? So I can never fill in that gap in between them. So if this started at the same point, then yeah, it would be continuous, but this would be a non-removable, right? Because it's a jump on that graph. So you're going to plug in the, like basically the x value where they change to see if it's continuous or not. So that was all of 187. And there's some practice on, I forget if it's on 188, 189 or not till next time. There's definitely some on 192.